Alright, so this is part 2 of rotational motion. In the last video, we essentially just went through the conversion between translational quantities such as distance, velocity, and acceleration, and we found their rotational equivalents. So angular displacement, which we know is an angle, and so that's theta, our angular velocity, which we know is omega, and our angular acceleration, which is alpha. And this is measured in radians, radians per second, and radians per second, respectively, okay? And using this knowledge, we went through and saw the changes between translational kinematic equations and the rotational equivalent of those kinematic equations. And then we essentially applied those to some quick problems. And for this video, we're essentially going to continue that theme and look at the rotational equivalent of mass, okay? So let's first define what we mean by mass. Usually when we talk about mass, we are talking about the amount of matter within an object. Now, this definition is technically correct. However, this is more of a chemistry definition, okay? This is more of a chemistry definition. In terms of physics, we are more interested in the way something moves. And so for physics, we can think of mass as an object's resistance to motion. Now, intuitively, this definition should make sense, right? We know intuitively that a heavier object is harder to move, right? So like a steel ball, like a shot put maybe, is harder to move than a tennis ball, let's say. And also, this makes sense when we consider Newton's second law, I believe, right? F is equal to ma. If a object is more massive, meaning it has more mass, we require a larger force to produce an equal amount of acceleration. And so, put more simply, if we want to achieve an acceleration, let's say of 3 meters per second, if we have a heavier object compared to a lighter object, right? This heavier object would require a larger force than this lighter object, right? To achieve an equal acceleration for both objects. And as we know, acceleration is both speeding up, slowing down, and changing direction. Alright? And so we refer to this property of an object's resistance to change in motion as an object's inertia. Okay? Now, it's important to note that mass and inertia are not the same thing. However, mass is a measure of an object's inertia. So, for rotational motion, we want to look at an object's rotational inertia. Right? And so our rotational inertia is an object's resistance to changes in rotational motion. And as earlier I described motion as speeding up, slowing down, or changing direction, right? So that would be spinning faster or spinning slower, or spinning clockwise to anti-clockwise, and vice versa. And for rotational inertia, we use the symbol I, right? Pretty simple to remember, I for inertia. And our rotational inertia have a couple of properties, one of them being that it's directly proportional to the mass of the object. Right, this makes sense from our previous definition, where our mass is the object's resistance to motion, and so our mass is a property of inertia. Now, rotational inertia also includes another aspect, which is how this mass is distributed across the object's center of rotation, and we can refer to this as r, and this quantity is squared in this case. And so putting it into words, r is the distance of the mass from the object's center of rotation. Okay? And so what that essentially means is that if the mass is distributed far away, the r value is going to be greater, right? And therefore our rotational inertia is going to be greater also. And the opposite is true. If the mass is distributed very, very close to the center of rotation, our r value will be going down, and therefore our rotational inertia will also decrease. So that's our r value. And from this, we can basically say that I is directly proportional to our mass times our r squared. And therefore, our rotational inertia is equal to some constant, let's say k, times our mass times our rotational inertia squared. Now for this constant k is equal to 1, and therefore I is equal to mr squared, right? Because if k is 1, then it essentially just disappears from the equation. So I is equal to mr squared. When all the mass is r distance away from axis of rotation. And so what that means is if we have a cylinder and this cylinder is going into the page right now, if all the mass of this hollow cylinder is on this outer edge, and where this distance is r, that means all the mass is r distance away, right? If this is our radius, and all the mass is on this outer edge, therefore, all the mass is r distance away from the center of rotation, which is this point right here. Oh, there we go, that point right there. Now this k value changes depending on the type of object that we're looking at, and some of the most important ones I'll go through for NCEA Level 3. So the first one I want to point out is a hollow cylinder, right? So let's see if I can draw a hollow cylinder. Let's make this slightly larger like this. There we go. So this is a hollow cylinder. Now this is a hollow cylinder, so basically the exact same scenario that I set up here, right? Where all the mass is on the outer edge. So we can simplify this hollow cylinder as having all the mass on the outer edge, and so this mass is r distance away, and therefore in this scenario, I is equal to mr squared, because k is equal to 1, right? However, if we use a solid cylinder instead, right? So solid cylinder. In this scenario, our I is equal to half mr squared. So you can see our k value is half now. Now, as you can see, just by comparing these two, we can see that the solid cylinder has a lower rotational inertia than the hollow cylinder. And that makes sense based on what we discussed up here, because the mass of the object is distributed not on the outer edge, but throughout the entire object, right? We have a reduced r value and therefore a reduced rotational inertia. Okay? Right, another one where we have a hollow sphere. Now, you can't really draw a hollow sphere, so let's just saying this is hollow. Okay, just trust me. That's a hollow sphere. Hollow sphere, like so, okay? And this has a rotational inertia of 2/3 mr squared, okay? And for this, we have a solid sphere. And finally, we have a solid sphere. And this has a rotational inertia of 2/5 mr squared. Now, for level 3, you don't need to memorize these, so don't worry about memorizing these. You can write them down, for sure, but they will be given to you in the exam. What's more important is your ability to discuss the differences between the two. Now, given this, we can jump now to Newton's second law. In the translational world, we have F is equal to ma. Now, in the rotational world, we can give our rotational equivalents. So we can say that torque is equal to I alpha. Now, we've already discussed alpha, where that's our angular acceleration, so we can see how that's the rotational equivalent of our linear acceleration. Torque is a rotational force, right? Right, we know that torque is force applied over a distance, and this distance is the distance between where the force is applied, right here, to its axis of rotation. Let's say this is a beam on a pivot, and this is the axis of rotation. If we were to apply a force up this way, we know the beam would travel in a circular path up this way, right? So torque is the rotational equivalent to force, and we've already discussed inertia and mass, and we discussed angular acceleration and linear acceleration in our previous video, okay? All right, so given this knowledge right here, a common excellence question that comes up is when we have to compare and contrast two different objects that have two different rotational inertias. So for this example, I'm going to use a hollow cylinder and a solid cylinder. However, this explanation can apply to any two objects. So in this example that I'm going to use, let's say we have a situation where we have a hollow cylinder being pushed down a slope, okay? And then we switch that hollow cylinder out for a solid cylinder going down the exact same slope, and this solid cylinder has the same mass and the same radius, okay? And we push down the solid cylinder down the slope. What you will find is that the solid cylinder reaches the bottom of the slope faster. The reason behind this is that the solid cylinder has a lower rotational inertia compared to the hollow cylinder, This means that if we apply the same force or the same torque to both cylinders, so torque remains the same, because the solid cylinder has a lower rotational inertia, its angular acceleration must increase. And therefore, as A is equal to R alpha, again, as both cylinders have the same radius, the linear acceleration of the solid cylinder would be larger than that of the hollow cylinder. And therefore, the solid cylinder reaches the bottom faster. So that explanation is all well and good. However, the part that we are missing is, why does the solid cylinder have a lower rotational inertia compared to the solid cylinder? We know by looking at the equation that the solid cylinder has half mr squared, however the hollow cylinder has mr squared, right? But why is this the case? So something that you've probably heard before is something to do with effective radius. I know I've definitely used this in some of the past exams I've gone through. You probably heard something along the lines of, when we switch to the hollow cylinder, the effective radius has decreased, blah, 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 blah. So what is this term effective radius? Like I said previously, our radius is the distance of the mass from the object's center of rotation, right? This right here. However, if you can imagine, we have a solid cylinder. The mass is distributed evenly throughout the entire cylinder. There is not just one point that we can point to where this is where all the mass is. The case is not the same for a hollow cylinder. Like I said, for a hollow cylinder, we can imagine that all the mass is at the outer edge. And so we can define that the mass is at this point, at radius r. We can't do the same for a solid cylinder. So this makes the comparison between hollow cylinders and solid cylinders very, very difficult. One thing we can do, however, is can we simplify a solid cylinder into a hollow cylinder that has the same characteristics? Now, because we know that hollow cylinders have a larger rotational inertia, this equivalent hollow cylinder of the solid cylinder is going to be smaller than the solid cylinder, right? So we have a solid cylinder, and this equivalent hollow cylinder is going to be smaller than the solid cylinder, right? Slightly smaller. And we know the rotational inertia of a solid cylinder is half mr squared, where this value right here is our r, okay? And we know the rotational inertia of a solid cylinder is mr squared, right? And we're going to call this r value r effective. So this is our effective radius, okay? So this right here is our r effective. Now, like I said previously, in this model, the solid cylinder and the hollow cylinder are equivalent, meaning they have the exact same rotational inertia and therefore have the exact same characteristics. That means their rotational inertia, like I said before, are equal, and therefore we can make them equal like this. Half mr squared is equal to mr effective squared. Now, their masses are the exact same, so we can cancel those out, and we get half r squared is equal to r effective squared. And therefore, our effective radius is equal to square root 1 over 2 times our original radius. And that is equal to 0.707 r, okay? So, the important thing to note is that our effective radius of our equivalent hollow cylinder is 0.707 that of the original radius. So our effective radius is a fraction of our original radius. So in an excellence question, when we say we are going from a hollow cylinder to a solid cylinder, and we say our effective radius has decreased, what we're saying is, if we were to model that solid cylinder as a hollow cylinder, the equivalent radius would be a fraction of that of our original radius, okay? So remember, this is purely a model, okay? We are not replacing the solid cylinder with this. We are modeling the solid cylinder as a hollow cylinder. Important thing to note, this whole discussion right here that I've done is not required for your excellence explanation. You can simply say the effective radius has now decreased. This explanation that I've given for you is purely for your understanding, but yes, for your excellence explanation, you can just say the effective radius has decreased, and therefore the rotational inertia has decreased, and therefore, due to there being the same torque applied, our angular acceleration has increased, and therefore our linear acceleration has increased. That's completely fine. So let's do a quick example question. Let's say I have a flywheel, And this flywheel is given an rotational inertia of 3.2 kg meters squared, right? So we don't particularly care if this is a hollow cylinder, a solid cylinder, whatever, we don't care. We are given its rotational inertia, and so we can apply the characteristics from there. And let's say we apply a 25 Newton force downwards, okay? And this force is going to cause the flywheel to rotate clockwise, right? Because we are applying a force at a distance from the pivot. And let's say this distance is 0.21 meters, okay? And let's say for this we want to find the angular acceleration, okay? So from our level 2, we should know that torque is equal to force times distance, and we are applying a force of 25 newtons at 0.21 meters from the pivot, or axis of rotation if you will, and therefore our torque is equal to 25 times 0.21, and this gives us a torque of 5.25 Newton meters. And because we know that torque is equal to I alpha, we know our alpha is equal to torque all over our rotational inertia, and therefore 5.25 all over 3.2. This is equal to 1.64 radians per second per second. Sweet as. Now, because we are applying a constant force, our rotational acceleration is therefore going to be constant. And this is useful because from here, we can use our kinematics right here to find out the radians it has turned through or its angular velocity. So now let's just finish off with a more complicated example. For this one, we're going to determine the rotational inertia of a flywheel. Okay, so let's draw our flywheel. Okay, and this radius distance right here is 0.2 meters, and we have a mass that is hanging off this flywheel. This is a known mass. We know the mass of this is 0.18 kgs. Okay, and we also found out that the acceleration of this flywheel is 1.2 meters per second downwards. Okay, so it's accelerating 1.2 meters per second downwards. So in order to calculate I, we need to go through a few steps. So with our knowledge of physics and Newton's third law, we know that there is a tension in this rope, and this is going to be a force pair, and that we can label as tension T. This tension is the tension that is going to supply the torque to the wheel. Okay, supply torque to flywheel. This is a crucial idea that most students mess up. A lot of students think it's the mass that produces the torque in the flywheel. It's actually not. It's the tension in the rope. So now, how do we find the tension force? Because we know the tension force is the force that supplies the torque. So we can do this by using some free body diagrams. Now we can see that the tension force is the force that applies the torque if we use some free body diagrams. So if we do a free body diagram of the flywheel, okay, so let's draw that free body diagram. We have a rope coming down, and that has a force that is pulling the flywheel into this direction right here. Now this force, as you can see, is the tension force. So we have the tension force pulling the flywheel down. So this free body diagram reveals the fact that the tension force is the force that provides the torque. So now what is this torque? Well, we can find that out by using the free body diagram of our mass. So if we have our mass right here, this is 0.18 kgs. I don't know why I put that there. Let's rub that out. Okay. And we have a tension force acting upwards, right? We can see that over here. And we obviously have a weight force acting downwards, right? That is the weight force of the mass. And let's say we take down as positive, right? The reason why we would do that is because the whole system is moving downwards, so we take down as positive to make our life easier. And so our net force is going to be our weight force minus our tension force, okay? Now, rearranging for our tension, we get tension is equal to our weight force minus our net force, okay? Now we know our weight force is equal to mg minus our net force, which we can say is ma, and this a value is our acceleration of 1.2 meters per second, and that's equal to our tension. So our tension is equal to our mass, which is 0.18, times 9.81, minus our mass again of 0.18, times our acceleration of 1.2, and this gives us a tension of 1.55 newtons. There we go. So like I said before, the tension is the force that applies the torque. And so because we know that our torque is equal to force times distance, where our force is the tension force, so TD, right? We can now work out our torque is equal to 1.55 times our distance of 0.2. This gives a torque of 0.31 Newton meters. There we go. Now, because we know our torque is equal to our rotational inertia times our angular acceleration, we can rearrange for our rotational inertia, and we get rotational inertia is equal to our torque divided by our angular acceleration. Now, we know our torque, but we do not know our angular acceleration. However, we know our linear acceleration, and we know our angular acceleration is equal to our linear acceleration all over our radius. And therefore, because we know our linear acceleration is 1.2 meters per second, and we know our radius is 0.2, we can work out our angular acceleration. So our angular acceleration is equal to 1.2 all over 0.2, and therefore this gives us an angular acceleration of 6 radians per second. There we go. And now plugging this into here, we get our rotational inertia is equal to 0.31 all over 6, and this gives us a rotational inertia of 0.052 kg meters squared. There we go. Okay, so that's it for rotational motion in level 3.